So we have started with this macro mechanical analysis of lamina. So before a discussion of this lecture, we have seen the basic concepts of macro mechanical. What is meant by micro mechanical analysis and macro mechanical analysis? Then what is meant by laminate and what is meant by lamina? That differentiate now all of we are familiar with. And with this, now we are observing the macro mechanical analysis of lamina. And for that purpose, we have taken the reference of analysis of mechanical element. At the same time, during last semester, we studied the solid mechanics and we have taken the reference of solid mechanics also. So, macro mechanical, what is concept of macro mechanical, that we have studied basically from solid mechanics and then lamina, so that we have seen the number of laminates comes together to form one lamina. Now, one of the different thing and interesting part of this discussion is that the types of materials. So during last one lecture we have started, we are discussing about the different types of materials. And with this, we have studied what is meant by isotropic material, what is meant by anisotropic material, and in between isotropic and anisotropic materials, we are observing now orthotropic, monoclinic, transversely isotropic, these materials. Is it okay? So one by one now, the type of materials we are going to study, and then during last lecture, we started with this concept of stress-strain relationship. Is it okay? So for stress-strain relationships, we have seen the two types of matrix, out of which one we have seen it is called as the stiffness matrix. Is it okay? So the stiffness matrix, and at the same time, one more relationship in between strain and stress. Because in case of relationship between stress and strain, the stress is equal to one matrix into strain, and that particular matrix which is multiplied to the strain is called as the stiffness matrix. Is it okay? So for the stiffness matrix, there are total 36 constants. So 6 by 6 like this matrix is there. Each and every stress is related with each and every strain. Then that kind of relationship will be given as totally anisotropic, because what we required is that whenever the material is isotropic, we have seen that this particular matrix which is represented with the help of stress strain relationship, and in case when that stress and strain relationships are given in terms of 1 upon E minus mu upon E minus mu upon E 0 0, so that 0 0 0 indicates that if I am multiplying with, if I want to identify the Ex epsilon x strain along x direction. So strain along x direction is related with each and every element like this, means first row into first column. That multiplication we are going to do here. So with this first row and first column, with this multiplication, P upon A minus, because all these things are not present here. If this is uniaxial type of stress system, in that case there is no relationship between other elements and this particular elements. In that case, epsilon x will be given as P upon E, which is a simple problem which we started in case of analysis of mechanics in second year, identifying the strain along the x-axis, that was calculated P upon A with simple manner. Similarly, while calculating this epsilon y, that is strain along y-axis, this row and this column, when we are going to multiply here, so only minus mu P upon A, by that way this epsilon y get calculated, because the system is uniaxial stress system. But if the system is not uniaxial, biaxial system, then P1 upon A, similarly P2, so P1 concept will be here, P2 will be here, and P3 will be here. That indicates that the forces are acting along x direction, y direction, as well as z direction also. If these values are also present here in the stress values, then that indicates, suppose in this region, whatever the zero is here. So if values comes here, that means for these first three zeros, first three places, whatever the load is given, that load that will be indicated, that will be given with the stress sigma 1, sigma 2 and sigma 3. That means these are the stresses along x, y and z axis. And if suppose at these three locations also stresses are present, that means the shear stresses are also present. Is it okay? Means apart from direct tensile loading, if additional some more loads are acting on that, then in that case it will be regarded as the shear stresses are also acting on that. So shear stress and shear strain, like this relationship will exist. There is shear strain and shear stress here. Is it okay? Then each and every row element and each and every column element that will get related if that particular forces are acting. Suppose shear force is present, shear force is acting, then definitely that will have the relation, that relation will be existed in between shear strain and shear stress. Is it okay? Likewise, here if we try to establish that relationship, then we will come to know that whether the material is isotropic, then whether it is uniaxial, biaxial or triaxial. Based on that, these values means values of these stress values that will depend upon uniaxial, biaxial, triaxials. The forces are acting in, shear forces are also acting in xyz direction. Then all these terms will get presented here. The strain that is always present irrespective of load. Suppose in one direction also force is acting, then strain values are present in all directions. Is it okay? However, that values may be zero if these are suppose uniaxial case. Is it okay? So like this, now we have understood the relationship between stress and strain, and which are uh, bonding with each other in matrix form. Is it okay? So this row and this columns, this multiplication, that is multiplied with each other with respect to this matrix form. Is it okay? So that is the advantage of matrix, to use the matrix, that simultaneously you will get all the strains. You will be able to calculate all the stress. Is it okay? So this is the example of uniaxial stress system. Is it okay? Now we are going further now on the type of materials. Is it okay? Now only we have taken the example of isotropic material only. But if the nature of the material is different, then with respect to that nature of the material, that relationship between stress and strain, that will vary here. Is it okay? Now, as far as concerned with this C11, C12, C13, C14, now I am going to compare each and every element with respective matrix which we have formulated by taking the example of uniaxial stress system. Is it okay? C111 is here 1 upon E. C22 is here minus mu upon E. So, if the material is suppose not isotropic, then how that relationship exists and how these different parameters are correlated with each other, that is the part of interesting to understand here. Is it okay? Then let us see here what is going to happen. Suppose this C11 into epsilon 1 is here. So C11 into epsilon 1, C12 into epsilon 2, C13 into epsilon 3. Likewise, this remaining 3, C14, C15, C16 into gamma 23, gamma 31 and gamma 12. This means whenever the multiplication of row with column is going to happen, then that multiplication of row into column. So for that, each and every element of the row and each and every element of the column that are related with each other. Is it okay? So total, how many number of constants, maximum number of constants, how many are possible here? So that is the answer is 36. Is it okay? Now see here that whenever we are considering the uh, simple isotropic material, then always we are considering the four elastic constants. So four elastic constants are E, mu, Z, K. E is the Young's modulus, mu is Poisson's ratio, G is shear modulus, and K is bulk modulus. So if that 4 parameters are known, then all parameters we can identify. We required only 4 parameters in that case, and out of which only 2 are known, then only remaining we can identify. Is it okay? We know the relationship between shear modulus, Young's modulus, and other elastic constants also. So maximum for elastic constants, but if 2 are known, then also for isotropic material we can identify remaining constants. Here in this case, what is going to happen if the material is not isotropic, and if the material isotropy of the material is changing, then exactly what is going to happen here? See, so these two matrices we are considering, out of which this is we have considered as the stiffness matrix. So stress into strain. In general, stress upon strain is Young's modulus, and E is considered to be elasticity stiffness. Elastic stiffness E is considered as, and that's why the correlation of this E, which is given with this particular matrix, which is represented by C11 to C16. All these elements are the representative of the stiffness matrix. So that's why stress into strain, like this stress is equal to something matrix into strain, then this matrix is called as the stiffness matrix. Likewise, whenever we are trying to establish the relationship between strain and stress, then exactly what is going to happen here? See, so for strain and stress relationship here, what we are getting? S11, S12, S23. So whatever the value of this C11, this the inverse of this matrix will be this S11 matrix, and it is called as the compliance matrix. Is it okay? So the matrix represented by C11 to C11 to C66, like this, with all these elements, is considered to be stiffness matrix, and the matrix represented by S11 to this S66 with these all elements it is regarded as the compliance matrix. So whenever there is a relationship between strain to stress, then that relationship between strain and stress, that is here correspondingly given by the compliance matrix. Is it okay? So here we can understand the difference between stiffness matrix and compliance matrix. As far as concerned with stress to strain relation, we are considering stiffness matrix. As far as concerned with strain to stress relation, here we are considering to be a compliance matrix. Is it okay? So here we can understand what is meant by compliance matrix. Is it okay? Then this relationship, in order to identify the different values here, what is meant by S11, what is meant by S2, S12, like this. If the material is isotropic material, then that stress value of S11 can be represented by 1 upon E. So S11, S22, and S33, all these the values of the diagonals, S11, S22, and S33, these diagonal values that we can, so this S11, S22, S33, these diagonal values that we can consider. Oh, this is value S11. So this particular value of S11, this particular value of S22, this particular value of S33, then all these three values are the diagonal values, S11, S22, S33, all three diagonal values which are shown here. So these values that are given as 1 upon E. Is it okay? So whenever we consider these diagonal elements here, and if material is isotropic material, as far as concerned with this isotropic material and all those diagonal values, so value it will be 1 upon E only. But if the type of material changes, then that is not going to remain as 1 upon E. So because in X direction Young's modulus will be different, in Y direction Young's modulus is different, in Z direction suppose Young's modulus is different. In that case, we can't say that S11 is equal to S22 is equal to S33 is equal to 1 upon E. But at that time, that is going to change here. Is it okay? So now by considering the case of isotropic material, and that material which is having the uniaxial stress system, in that case this S11 we are considering 1 upon E only. Is it okay? So like this, if we compare this S11 with this particular matrix, because we know that for uniaxial, biaxial and triaxial stress system, how the stress and strains are related with each other. If we consider here sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z, and this strain, shear strain, likewise shear stress tau yz, tau zx, and tau xy, then in that case, this particular row elements and these column elements are interrelated with each other. The first row element with this first column element, that is multiplied here in order to identify the relationship between this row and column elements. So sigma 1, sigma 2, sigma x, sigma y, sigma z, likewise tau yz, tau zx, and tau xy. Like this relationship will get established in that way. So same thing, if we take into consideration here, we will come to know that here if we consider, say, for this S22, this particular value is considered here as S22, here is S22, here you can consider the S22. So S11, S22, S33, because S11, S12, S13, S14, S15, S16, likewise S21, S22, S23, S24, S25, S26. Likewise here S31, S32 and S33. So likewise these three elements which are shown here. So these three elements which are shown here, that is considered to be S11, S22 and S33. So here we can understand all three are equal. S11, S22 and S33 are equal. However, as far as concerned with this S12, now what is going to happen, that will study later on. But S11, S12 and S13, likewise, if these are same, then here these are 1 upon E. Okay, so we try to understand S11, S22, S33 is equal to 1 upon E, why it is considered in case of isotropic material. Okay, so here isotropic material, for that what is S11, what is these values, so that we should understand here. Is it okay? So here we can study, we can understand this particular thing, S11, S22, S33. Is it okay? So likewise, now if we come to S12 now, see here. Now we are coming to S12. So this is S11. We have recently we have seen that what is meant by S11, S22 and S33 in this diagonal direction. But this is S11, then this is S12. Here we can see S13. Is it okay? S12, S13. So here we can see which sign. If we take the sign is negative sign. Is it okay? Here we can see this sign is negative sign. And this particular matrix we have derived. That's why we know. We have derived this matrix. Is it okay? So here we can see how while deriving this particular matrix, how we have taken the reference of biaxial stress, triaxial stress system. Is it okay? Now here if we try to understand which sign the things, then we will come to know this is S12, because S11 is 1 upon E, S22 is 1 upon E, S33 is 1 upon E. So S12, S13, S31, S here S3, S21, S22, S23. Is it okay? So these three elements, like triangular matrix and this like this triangular matrix, if we consider this 3 by 3, then these three elements which are present here and these three elements here, S12, S13, S21, S23, S31, S32. Is it okay? All these six elements are now equal. Initially, these diagonal elements were equal, and these diagonal elements are represented by S11, S22, S33, and that is given as a 1 upon E. But if we consider the remaining six elements now, then S12 here, which is represented here, S1, S3 is here, S21 is here, S23 is here, S31 is here, S32 is here, and all these are what we can say here. These all are minus mu upon E. Is it okay? So see, these are S21. What is meant by this S21 that we can understand here? This is S21. This is S12, S13, S31, S32, and this is S23. Is it okay? So here we can understand these three elements and these three elements. So these three elements, if we compare with our equation which we have derived here, then we will come to know how these elements are identified here, how these are calculated here. So as far as concerned with this S11, S22 and S33, the answer will be 1 upon E. And as far as concerned with this S12, S13, S21, S23, S31, S32, answer will be minus mu upon E. Is it okay? And then there is one last concept, that is these three elements. Now we should understand these remaining three elements. So before going to these last three elements, now we will see here how these three elements are there. So here we can see now these three elements. Is it okay? So one by one we will go. The first of all, this S44, then S55, then S66. Is it okay? See, I try to understand here. S44, S55, and S66. How these three elements are here on this particular line. Here we can understand here. S44, S55, S66. Like these three elements are here. Then S44, S55, and S66. So if we compare this particular value with this matrix which we have derived based on our assumption, we'll come to know what is meant by this S44. So this particular value is S44, this particular value is S55, this particular value is S66. Is it okay? So S44, S55, S66. See, so which are present here, S44, S55, S66. Then definitely we will consider here as S44, S55, and S66 are nothing but 1 upon G here. Is it okay? Here we can understand these different elements present now here. So we will come to know one by one. Once again we will repeat the things because that is very important and we should know that properly. This particular element 1 upon E which is shown here, what this particular part will be considered S11. This will be considered to be S22. This will be considered to be S33, and by that way S11, S22 and S33, all these three are equal to 1 upon E. Is it okay? Then as far as concerned with the remaining elements, S12, so this is S12. Is it okay? So now we will try to understand remaining 6 elements. S12, then this is S13, then this is S21, S23, S31, S32. Is it okay? So all these 6 elements are given by minus mu upon E. And then the remaining 3 elements, out of which this one is S44, S55, and S66. Is it okay? So all these are considered to be, so like this particular elements. So strain to stress, this particular relationship is given with the S means compliance matrix. Is it okay? So the C shows stiffness matrix and this S shows compliance matrix. Is it okay? So strain and stress, how these are correlated with each other as far as concerned with isotropic material with stress strain equation. the compliance matrix S11, S22, S33 is given by 1 upon E. The 6 elements which earlier now we discussed is given by minus mu upon V, and 3 elements S44, S55, S6 is given by 1 upon Z. Is it okay? So, in short, all these elements, so for that purpose, to describe this relationship between stress and strain, here one common thumb rule is given that stress I is equal to summation from J to 6 Cij epsilon J here, where I is equal to 1 to 6. Okay. I represents 1, 2, 3, 4, 5, 6. Now see, this is very important, this relationship, because we should know that particular. See here, we have given here this relationship. See, now you can see for each and every I is equal to 1 to 6 here. And when I put here I is equal to 1, here also Ci means C1. But if j is equal to 1 to 6, so for this, if we repeat this sigma 1, then j is equal to 1 to 6 means for 1, I will get here C11 epsilon 1. Then C12 epsilon 2. C13 epsilon 3. C14 epsilon 4. C15 epsilon 5. C16 epsilon 6. So addition of them is okay. Likewise, means suppose I am trying to understand the stress from strain. Here I am identifying the stress from strain. Then in order to describe this particular concept of stress, let us understand here this sigma 1. Now I have marked this sigma 1 here. I am marking this C11 here, C122 here, C. So all this C now for the first row I am marking here. So with this C here 1, 5, 1, 6, each and every is multiplied with epsilon 1. So one another way through which we can represent this matrix is this row and this column here. Is it okay? See here. C11 epsilon 1, C12 epsilon 2, C13 epsilon 3, C14 gamma 23, then C15 gamma 31, and C16 gamma 12. So the particular row and this particular column. With that multiplication, we can identify the sigma 1. So, but the common way how which are representing that, so this is one format through which we are representing. So sigma I represents I is equal to 1. In order to identify this sigma 1 here, I want to multiply this each and every row element by the column element, where I1 is going to remain constant. 1, 1, 1, 1, 1, that is going to remain constant here. But this j is going to vary here. And for that purpose, the common equation in this format has been written that represents that I is 1 only. I is going to remain constant as 1. For j, it is going to repeat for 6 times. Is it okay? So we may consider this as iteration. Is it okay? So j is iteration. So j is going to repeat from 1 to 6 here. And we are going to make this summation of that, because here also we know that C11 into epsilon 1, C12 into epsilon 2, C13. We are multiplying and making addition also. The corresponding element of the row we are multiplying with corresponding element of the column, and then we are taking the addition of them. So same thing is represented here with this summation sign. So sigma 1 is nothing but summation of j is equal to 1 to 6 here. So this j is iteration from 1 to 6, which is going to change from 1 to 6. And for every j, when epsilon is there, so 1 to 6 times that is going to repeat here. And for each and every j, this sigma 1 will be addition of these two elements. Then sigma 2 is addition of these two elements. For sigma 3 again addition of these three elements. So like this 6 times these stress values will get calculated with these summation values. Is it okay? So this particular equation is nothing but this total matrix. Is it okay? So representing the total matrix in that format. So equation 2.25 that is only represented with this 2.28 only. Is it okay? So this particular equation 2.28 represents nothing but the matrix 2.25. Is it okay? So some contracted notations are used here. So we should do understand the meaning of contracted notation. What do you mean by contracted notation? Because earlier we have used this tau shear stress 2 3 3 1 1 2, but now we are using the contracted notations as sigma 4, sigma 5 and sigma 6. Is it okay? Because earlier whenever we are using this particularly here tau 2 3 tau 3 1 tau 1 2, that was used the notations here, but contracted notations now we are going to change, and that changed notations are we are representing sigma 4 besides this tau 2 3, sigma 5 besides this tau 3 1 and sigma sigma 6 besides this tau 1 2. Similarly, the shear strain values means epsilon 4, epsilon 5, epsilon 6, sigma 4, sigma 5, sigma 6 will be the shear stresses and shear strains. So that we do understand here. Is it okay? What is meant by sigma 4, sigma 5, sigma 6, epsilon 4, epsilon 5, epsilon 6. So these are the stresses and strains. So shear stresses and shear strains. So for that, these particular notations are used here. Is it okay? So all of we know that whenever identifying the strain energy, we always take the addition of this particular stress, corresponding stress into strain multiplication, and we are taking half of that. Is it? So half summation I is equal to 1 to 6 sigma I epsilon I is here. Is it okay? So this equation 2.28 like this is represented here, and this particular substituting Hooke's law from 2.28 in 2.30 means for strain energy, this particular equation is written in that way, and then by partial differentiation here dou W and dou epsilon I dou epsilon J like this. Here we can understand the concept of solid mechanics is once again here it is shown here. So what we understand from all these processes from this particular today's lecture is that what is meant by compliance matrix, what is meant by stiffness matrix, the relationship between stress and strain with these 36 constants. Is it okay? So when the material type changes, then how many number of constant we should take into consideration, that part comes into existence, and accordingly we should have to make that relationship with each other. Now let us understand the concept of isotropic material. So with this concept of isotropic material, we will stop this lecture. So anisotropic material means what? See, we consider this particular relationship between stress and strain, and these are the number of constant through which this stress and strains are related with each other. If number of these elements are less, if number of dependency on the element is less, then the material is coming toward the isotropic format. But if suppose the Young's modulus in x direction is different, y direction is different, z direction is different, then always the dependency changes, because while calculating the Poisson's ratio, whenever we are calculating the Poisson's ratio, we are taking the lateral strain to the longitudinal strain. And lateral strain to longitudinal strain, for that purpose, if Young's modulus of lateral direction and longitudinal direction is different, then with one Poisson's ratio it is not possible. Is it okay? So what is going to change? E1, E2, E3 if it is going to change. Likewise, now we will have to introduce 3 Poisson's ratio. So three Young's modulus, three Poisson's ratio, three shear modulus, three bulk modulus likewise. For each and every direction, all these parameters are going to change, and that's why the type of material for which the number of independent constant, elastic constants. So see here, it is very important because for MCQ also for university number of times asked this question. For anisotropic materials, how many independent parameters are required? And the answer is 21. Is it okay? Do understand and do keep in mind that 21. Is it okay? So 21 independent constants are required in general in isotope. The material that has 21 independent elastic constant at a point is called as an anisotropic material. Is it okay? In order to understand the concept of anisotropy, these 21 independent elastic constants, so that we should understand, and this will be the anisotropic nature of the material. Is it okay? So see here, this is one direction, this is two direction, and this is third direction. So if we consider this as x direction, y direction, and z direction, then what is going to happen? Suppose 1 and 1 dash, 2 and 2 dash, and 3 and 3 dash that are shown here. Is it okay? So once these constants are found for particular point, the stress and strain relationships can be developed at that point. Is it okay? Now this constant can vary from point to point if the material is non-homogeneous. Even if the material is homogeneous, one needs to find these 21 elastic constants. Means see, one more parameter is now added here. As per as concerned with this isotropy, anisotropy is one more different thing, and homogeneity, for that non-homogeneity is also again different thing. So in case of composite material, there may be the chances of non-homogeneity also, because if suppose layer of matrix is not uniform from location to location, suppose the reinforcement are not placed uniform at point A, suppose reinforcement thickness is different, and at point B reinforcement thickness is different, then there may be the chances that material is non-homogeneous, and it is we will consider as non-homogeneous. So non-homogeneous and anisotropic, that is very complicated case. So here we have assumed that material is anisotropic but homogeneous. Is it okay? In case if the material is homogeneous and anisotropic, then one needs to find 21 elastic constants analytically or experimentally. So natural and synthetic material, for that purpose there is certain material symmetry. Is it okay? Elastic properties are identical in the direction of symmetry, because symmetry is present in internal structure. For naturally that advantage we are always getting. Is it okay? So the simplified Hooke's law relationship for various types of elastic symmetry, for that purpose we should try to understand here what is meant by this anisotropy and how this six, now see here we have considered here as 21 independent elastic constants are there. Is it okay? So try to understand here, if the material properties in this above in this direction, if suppose it is same as in this direction, then what is going to happen? Then what is going to happen? Am I audible?
Yes, sir.
So we should understand anisotropic, the concept of anisotropic. So for the next lecture, we will try to see what is meant by monoclinic type of materials and what is meant by this orthotropic material. So monoclinic and orthotropic, that discussion we will carry for the next lecture. But for today's lecture, we should